Now let's compare the strength of the two here. Is we know that the force between two charges, which is a Coulombic force, is 1 over 4 pi epsilon naught and Q1 Q2 over R squared. And in case of the magnetic field, the force which is magnetic in nature is equal, as we have calculated this thing earlier. This is mu naught I over 2 pi, mu naught I over 2 pi r the field, and here it was mu naught I1 I2 as we have calculated earlier over 2 pi r, and we have a mu naught I here and we have r here, 4 pi r. So this is a constant which is dealing the electrostatic force, defining its magnitude, and this is we call it Ke, the constant, and here this is the constant which is dealing the magnitude of magnetic force here. So this is a constant mu naught over 4 pi, and here we call it constant, like let's say call it Kf, K for E and K for M here, the magnetic field constant. Now we know one thing between the two. When we do combine the two, then the speed of the electromagnetic wave is we have this thing C 1 over mu naught epsilon naught this. So I can write that C squared is 1 over mu naught epsilon naught. Now if I divide the two constants, like 1 over 4 pi, and this if I divide like this, that 1 over 4 pi epsilon naught, like the two constants Ke over Km, then this is 1 over 4 pi epsilon naught, and this is mu naught over 4 pi. So 4 pi, it will go up here, and we have the 4 pi cancellation, and this is 1 over mu naught epsilon naught. 4 pi will go up, epsilon naught down here, and 1 over mu naught epsilon naught is equal to C squared. Means the ratio of the constant of the two forces is C squared, and this thing is equal to, we know about C, 3 10 power 8 and square, so approximately this is 10 to the power 16. So the ratio of the two forces here is 10 power 16. It means that the strength of the electric force is 10 power 16 times greater than the magnetic force, and this is for the non-relativistic speeds. We will explain this thing in a while. Non-relativistic speed. But what if things are relativistic? So I can see this thing here. I can compare it from the other way around as well. Like Ke is approximately 10 to the power 9, while mu naught is roughly 10 power minus 7 in their standard SI units. But when I divide KE over KM, then 10 power 9 plus 7, and it will make 10 to the power 16. So this is for the non-relativistic speeds. Basically here we are having Fe over this FERK over Km. Here is C square, but here we have by default taken the V equal to 1. This is basically C square over V square. So V we have taken is 1, and that's why it is equal to this. If we write for the non-relativistic speeds like F, and this is E, this is divided by F and M, the magnetic, we can write FB, but as we are going on with magnetic, electric, and magnetic, this is approximately C squared over V squared. And if I say that V is approximately C, which is the relativistic speed, then Fe over Fm or Ke over Km will become comparable. So this is Ke, or we write Km, or we write Fe, Fm magnetic. So they are comparable here when it is a relativistic. So a charged particle moving at a normal speed, non-relativistic speed, the electric force is 10 power 16 times greater than the magnetic force or the magnetic strength. But if that particle starts moving at a relativistic speed comparable to the speed of light, then the two forces, or the strength of the two forces, becomes equal. So this is a comparison between the the electrostatics and the magnetostatics. Yet we can write this thing in another form as well, that about this one is we have the divergence of E equals rho over epsilon naught, and divergence of for E, if I write minus del V, then this thing implies that minus del square V or del square V is equal to minus rho over epsilon naught. So this is in the form of Laplacian. The del square, the Laplacian of V is minus rho over epsilon naught. Similarly here, when I do write this thing, then in the same analogy I can write for the magnetic potential that the Laplacian of A is equal to, as it is 1 over epsilon naught, so this will become mu naught, and is over there is rho, so we have J here. If I want to write this thing in the form here, means how this can be derived, so I can go to this equation del cross B, and for B I write this thing, for B I write del cross A. So it will be del cross A, and when I open that identity, then I will get at one point the del square, and at the other point del dot A, and del dot A is 0 because the magnetic vector potential is not diverging, and then I will get del square A equal minus mu naught G. So when they are in the form of potential, then their analogy becomes even more visible, that they are almost seems equivalent here. So now here for when we consider the sources of the two, here the source is charge, there the source is current. We will not go to the situation that current is charge per unit time, means again it is charge. But for the sake of keeping the two is different, like electrostatics and magnetostatics, because the reality is that there is nothing called magnetic field or magnetic induction. It is all the varying electric field. But for the sake of this discussion, we are calling it magnetostatic, and its source is current, is from after the legacy of Ampere. So here, then their field lines start and they end. Their field line don't start and end, they are continuous. Here we are having the another thing that we can discuss here, that from the field detection point of view, electric field detects stationary charges. It can detect stationary charges, but magnetic field can't detect stationary charges. It only detects moving charges, means currents. And if we do compare their energy densities, then in the electric case, the energy density is given by half epsilon naught E square, and in case of the magnetic field, this energy density is half, but epsilon naught will come is mu naught and then B squared, the magnetic field intensity. If we consider their forces, so forces here, we have the electric force equals to charge times the electric field, and here the magnetic force, the Fm, the magnetic force is charge times V cross B. The motion or the velocity of the particle is a cross product with the magnetic field. So here, although there are this is not part of the comparison, but is a general discussion. We have like some open questions. Like there are no magnetic monopoles, or there are not or no isolated magnetic monopoles, and yet the complete unification of the forces is yet to be done, because the gravity and the nuclear force can't be combined with each other. Another open question, the quantum mechanical nature of the electromagnetic interaction is not is to be further explored, and it's a topic of quantum electrodynamics, like studying their nature, and specifically at extreme conditions things are not clear. Like extreme condition mean when we are having very high energies, or we are having very short distances, then the quantum nature of the electromagnetic interaction is not clear. High strength of fields, high energies, less very short distances. So these things are the open questions uh, we have to address. So I hope that this much is sufficient for the comparison of electrostatics and magnetostatics.